The void of space is not empty, it crackles with an unseen energy, a seething ocean of potential hidden just beneath the fabric of reality. These are quantum fluctuations, the engine of possibility for our entire cosmos. By the end of this journey, you will understand how these tiny tremors hold the keys to the universe's greatest mysteries. We will explore how microscopic ripples gave birth to galaxies and whether our entire reality might be a cosmic projection. What single mystery of existence feels most profound to you? This restless energy has a name, the zero-point energy field. Think of the void not as a still, black emptiness, but as a vibrant ocean at its absolute ground state. Even at the temperature we call absolute zero, where all classical motion is supposed to cease, this quantum sea never rests. The reason for this perpetual simmer comes from a fundamental rule of reality, the Heisenberg uncertainty principle. This principle tells us that on the tiniest scales, we can never know everything with perfect precision. A particle can never be completely still and have a perfectly defined energy of zero. There is always a tiny, inherent jitter, an unbreakable hum of activity. This quantum rule forces particles to engage in a fleeting, ghostly dance. Pairs of virtual particles, one of matter and one of antimatter, borrow energy from the vacuum for an impossibly brief moment, flickering into existence only to annihilate each other and vanish back into the background hum. This is not just a mathematical idea, it produces real physical forces we can observe. The most famous demonstration is the Casimir effect. Imagine two perfectly smooth, uncharged metal plates placed parallel to each other in an utter vacuum, spaced only a microscopic distance apart. In the vast space outside the plates, a rich spectrum of quantum fluctuations can push on them, but in the narrow gap between the plates, only fluctuations of certain wavelengths can fit. This creates a pressure imbalance, with more virtual particles pushing from the outside than from the inside. The result, the plates are gently, but measurably, pushed together by the sheer pressure of empty space itself. It is a direct signature of the zero-point field, a tangible force born from nothing. This ghostly dance of particles in the void holds a staggering implication that the grand architecture of our universe was born from the smallest of seeds. During the universe's first fleeting moments, a period of hyper-expansion called inflation stretched these microscopic quantum ripples to astronomical proportions. Imagine a tiny wrinkle on the surface of a balloon, then suddenly that balloon inflates to the size of a galaxy. That wrinkle, now enormous, is no longer a tiny imperfection. It is a cosmic landmark. This is precisely what happened to those quantum fluctuations. As space itself expanded faster than light, it locked in these tiny density variations, regions that were ever so slightly more or less dense than their surroundings. These minute differences became the blueprint for everything to come. They were the gravitational seeds sown across the cosmos. Over billions of years, gravity patiently worked on these seeds. A patch of space with just a little extra density had slightly stronger gravity, pulling in more matter from its surroundings. This made it even denser, strengthening its pull in a powerful feedback loop. These seeds collapsed under their own weight, eventually forming the first stars, then galaxies, and the vast cosmic web of filaments and voids that we see mapped across the sky today. The most compelling evidence for this profound link between the quantum and the cosmic is written in the oldest light we can see. The cosmic microwave background radiation is a fossilized snapshot of the universe when it was just 380,000 years old. This afterglow of the Big Bang is not perfectly uniform. It is speckled with tiny temperature variations, hotter and colder spots that form a specific pattern across the entire sky. That pattern is a perfect fingerprint, a direct imprint of those initial quantum fluctuations stretched across the heavens. The very wrinkles we see in that ancient light are the amplified quantum jitters from the dawn of time, the origin points for galaxies like our own Milky Way. This ancient light reveals a cosmic blueprint, but what if even space-time is not what it seems? A truly radical idea suggests that our universe, with all its depth and dimension, might be a magnificent illusion. This is the holographic principle. It proposes that our seemingly solid three-dimensional reality, including every star, planet, and quantum fluctuation, is actually a projection from a two-dimensional surface at the very edge of the cosmos. The theory finds its roots in the strange physics of black holes. When scientists studied the properties of these gravitational monsters, they discovered something astonishing. The amount of information or entropy a black hole contains is not proportional to its volume, as you might expect. Instead, it is directly related to the surface area of its event horizon, the point of no return. This was a profound clue. It hinted that all the information needed to describe everything within a black hole could be encoded on its two-dimensional boundary. The holographic principle takes this startling notion and applies it to the entire universe. In this view, our cosmic home is like a giant cosmic hologram. Think of the hologram on your credit card. It appears to have depth and volume, a three-dimensional image you can almost reach into, yet all that information is stored on a flat, two-dimensional piece of plastic. What if our universe operates on a similar, unimaginably vast scale? The quantum fluctuations we have been exploring, the very seeds of galaxies, might not be fundamental randomness at all. They could be the visual static, the pixelation, that emerges from information being processed on the cosmic horizon. Just as a computer screen has a finite resolution, spacetime itself may have a fundamental pixel size, and the quantum jitter we observe is the result of that underlying data processing. This means the empty space around you is not smooth and continuous. It is more like a brilliantly rendered simulation, with its apparent smoothness hiding a fundamental graininess. The implications are staggering. If true, the holographic principle would mean that the fundamental laws of physics do not operate in the three-dimensional space we experience, but on a distant, two-dimensional surface we can never see. Our reality in all its rich detail is a projection, a shadow cast by the interactions of data on the edge of everything. This cosmic hologram might not be the only projection in existence. Our entire universe could be just one bubble in an infinite, frothing ocean of reality, a concept known as the multiverse. The mechanism thought to drive this endless creation is a runaway process called eternal inflation. Picture the initial burst of inflation that shaped our cosmos not as a single, finished event, but as a chain reaction that never truly stops. In this model, the fabric of spacetime is in a state of hyper-expansion, a cosmic energy field stretching faster than light. But this expansion is not perfectly smooth. Random quantum fluctuations, those tiny tremors in the quantum field, act as cosmic triggers. When a particularly large fluctuation occurs in a local region, it can kick that patch of spacetime out of its hyper-expanded state. That region then settles down, cooling rapidly to form what we would call a bubble universe, a stable pocket of reality like our own. The breathtaking part is that this process is eternal. While one region settles into a bubble, the surrounding spacetime continues its frantic inflation, providing an infinite backdrop where new quantum fluctuations can, and do, constantly trigger the birth of new universes. Our entire cosmic history, from the Big Bang to the present day, is just the story of our local bubble. We are living inside one frothing droplet in a boundless cosmic foam. Each of these budding universes inherits its own unique properties from the specific quantum fluctuation that gave it birth. This means the fundamental constants of nature, the strength of gravity, the mass of an electron, could all be different in other bubbles. In most of them, the conditions would be wildly inhospitable. Some might collapse instantly, others might be filled with nothing but radiation, unable to form atoms or molecules. This provides a potential answer to one of the most profound puzzles in science, the apparent fine-tuning of our universe for life. The constants in our cosmos seem perfectly calibrated to allow for stars, planets, and ultimately, us. The multiverse theory suggests there is no grand design behind this perfection. We simply exist in one of the rare bubbles where, by pure chance, the numbers came out right. It is a humbling and expansive thought that our entire reality might be a statistical fluke in an infinite ensemble of failed cosmoses. This idea that reality depends on your perspective reaches its most startling conclusion with a phenomenon known as the Unruh effect. If you are floating motionless in the void of space, you would confirm the vacuum is empty, a silent, cold nothingness, but if you were to fire your rockets and accelerate, an extraordinary change would occur. From your new, accelerating perspective, the empty void would no longer feel empty. Your ship's sensors would register a warm glow of particles, a thermal bath of radiation filling the space around you. This is not an illusion. For you, the accelerating observer, these particles are completely real, yet an astronaut floating at a constant velocity nearby would still see and measure nothing but a perfect vacuum. Both of you are correct in your own reference frames. The particle content of the universe is not a fixed, absolute reality. It is a relative one, deeply tied to your own state of motion through spacetime. The reason for this bizarre effect lies in the nature of the quantum vacuum and something called a particle horizon. When you accelerate, you are effectively creating a horizon, a boundary in space that you can never receive information from, much like the event horizon of a black hole. This motion through the seething quantum field changes which fluctuations you can interact with and perceive. The gentle, uniform hum of the zero-point field, which appears as nothing to a stationary observer, gets shifted and distorted from your accelerating viewpoint. What was a quantum jitter resolves into what you experience as real, warm particles. This is not just a mathematical curiosity. The Unruh effect provides a breathtaking bridge between Einstein's theory of relativity and the quantum world. It demonstrates that the very concept of a particle is not fundamental. What one observer measures as empty space, another, moving in a different way, will measure as a swarm of real particles. The universe's building blocks are not simply there, they emerge from the interaction between the observer and the underlying quantum field. This forces us to ask a deeply unsettling question. If particles are not absolute, then what in our reality truly is? This strange dependence on perspective offers a clue to one of the most elegant and devastating ideas in modern physics. Stephen Hawking made a startling prediction about black holes, those regions of spacetime where gravity is so strong that nothing, not even light, can escape. He realized they are not completely black, they glow, they radiate, and they slowly evaporate into nothingness, all because of quantum fluctuations at their edge. The mechanism is a direct, if extreme, consequence of the particle pairs we have already met. Normally, when a virtual particle and its antiparticle partner flicker into existence, they annihilate each other almost instantly. But near the event horizon of a black hole, the point of no return, the intense gravitational field can tear this pair apart. Imagine one particle forms just on the cusp, outside the horizon, while its partner forms just inside. The particle inside is forever lost, swallowed by the black hole's immense gravity. Its partner, however, is now free. With nothing to annihilate with, it escapes into space, carrying away a tiny amount of energy. This energy has to come from somewhere. It is stolen from the black hole itself. Each time this happens, the black hole loses an infinitesimal fraction of its mass. Over unimaginable eons, this slow, steady trickle of escaping particles, now known as Hawking radiation, causes the black hole to shrink and eventually vanish. A cosmic titan capable of devouring stars is ultimately defeated by the quiet hum of the quantum vacuum. This beautiful theory, however, created one of the most profound puzzles in physics, the black hole information paradox. In our universe, information is never truly lost. If you burn a book, the information in its pages seems destroyed, but in principle, a being with godlike powers could collect every particle of smoke and ash, trace every photon of light and heat, and reconstruct the exact text. The information is merely scrambled, not erased, but a black hole presents a different problem. When matter falls in, it carries information with it, the specific configuration of particles that made up a star, a planet, or a book. According to Hawking's original calculation, the radiation that the black hole emits is purely thermal, a featureless, random glow. It carries no information about what fell in. So, if the black hole evaporates completely, what happens to that information? Is it truly, permanently erased from the universe, violating a fundamental law of quantum mechanics? Or is it somehow encoded, in an incredibly complex way, in the Hawking radiation itself? This paradox pits the smooth, deterministic laws of general relativity against the jittery, probabilistic rules of quantum mechanics, forcing physicists to question the very nature of reality and whether information is truly the most indestructible thing in the cosmos. This staggering difference in energy is one of the most profound failures in our understanding of physics. We call it the cosmological constant problem. The calculations from quantum field theory give us a number for the vacuum energy, a value so immense it defies comprehension. If this theoretical prediction were correct, the sheer repulsive force of this energy would have blown every atom, every star, and every galaxy apart in the universe's first instant. Space itself would have expanded with such ferocious speed that no structure could ever have formed. Yet, when we look out at the cosmos, we see something entirely different. The actual energy driving the universe's expansion, what we call dark energy, is not just a little smaller, it is 120 orders of magnitude weaker. To grasp that scale, imagine the difference between the size of a single proton and the size of the entire observable universe. That is the chasm between our prediction and reality. How can our best theory be so spectacularly, monumentally wrong? This is not a minor oversight. It is a screaming signal that we are missing something fundamental. Physicists have proposed several paths to a solution, though none are yet confirmed. One elegant idea is supersymmetry, a theory that posits every known particle has a hidden superpartner. In a perfectly supersymmetric universe, the contributions of particles and their partners to the vacuum energy would cancel each other out exactly, leaving a net of zero. The problem is, we see no evidence for these superpartners in our experiments. If they exist, this symmetry must be broken, meaning the cancellation is imperfect, leaving behind the tiny wisp of energy we observe as dark energy. Another, more philosophical solution comes from the multiverse concept. If an infinite number of universes exist, each with a randomly determined cosmological constant, then only in the rare ones where the value is almost zero could galaxies, stars, and life ever form. We, of course, find ourselves in such a universe. This is the anthropic principle, the idea that the constants we measure are what they are because they allow for our existence. It is a compelling argument, but for many, it feels like giving up on a deeper, more satisfying physical explanation. Ultimately, the cosmological constant problem stands as a central mystery, a glaring clue that any future theory uniting quantum mechanics and gravity must solve if we are ever to understand the true nature of our cosmic home. This chaotic underpinning of reality has a name: spacetime foam. The physicist John Wheeler proposed that if we could peer down to the very smallest possible scale, a distance known as the Planck length, the smooth stage of spacetime described by Einstein would vanish. In its place, we would find a seething, turbulent ocean. At this fundamental level, the geometry of spacetime itself is subject to violent quantum fluctuations. The very concepts of before and after, or here and there, lose their meaning. Wormholes, tiny tunnels connecting disparate points, would blink in and out of existence. Virtual black holes, minuscule gravitational pits, would form and evaporate in a frantic, endless dance. The fabric of the cosmos would not be a calm, continuous fabric, but a dynamic, complex froth. A powerful analogy is the surface of the ocean seen from a great height. It appears perfectly smooth and flat, a serene blue sheet, but descend to the waves themselves, and you find a churning chaos of bubbles, foam, and collapsing water. Our reality from our grand human-scale perspective is that calm, distant view, but at its heart, it is all ocean foam. This idea creates an immense challenge for the holy grail of modern physics, a theory of quantum gravity. Einstein's general relativity depends on a smooth, continuous spacetime, a well-defined stage upon which the cosmic drama plays out, but spacetime foam tells us this stage is an illusion, a statistical average of unimaginable turbulence. How do you write the laws of gravity for a universe where the very arena of physics is constantly bubbling and boiling? It suggests that our fundamental theories are not wrong, but that they are approximations, like describing a foam only by its average density. The quest for a deeper theory, one that can embrace this chaotic foundation, continues, forcing us to question if smooth space and time are merely comforting stories we tell ourselves about a far wilder truth. Perhaps the strangest interpretation of all gives these quantum whispers a voice and a purpose. The transactional interpretation of quantum mechanics reimagines the entire quantum world as a cosmic marketplace of negotiation. In this view, a quantum event, like an atom emitting a particle of light, is not a random, isolated occurrence. It begins when the emitter sends out an offer wave, a kind of potentiality that ripples forward through time. This wave travels until it encounters a possible receiver, an atom that could absorb that very particle. That receiver then sends a response, a confirmation wave, backward through time, echoing all the way to the original emitter. Only when this two-way handshake is completed across the fabric of spacetime does the particle of light actually come into existence. The probabilistic nature of quantum mechanics, the famous idea that we can only predict the odds of an event, arises naturally from this process. The emitter sends out countless offer waves to all possible destinations, but a particle is only truly created when one of those offers is confirmed. This provides a stunningly intuitive picture for the spooky phenomenon of quantum entanglement. When two particles are entangled, the confirmation wave from a measurement on one particle can instantly lock in the state of its partner, because that handshake has already been negotiated across time and space. The quantum fluctuations we see in the vacuum could be the faint echoes of these constant, unresolved negotiations, a sea of offer waves searching for a confirming handshake. This interpretation challenges our deepest assumptions, suggesting that the future can reach back to influence the past, weaving causality into a single, non-local tapestry. This speculative leap brings us to a profound crossroads where physics meets philosophy. The participatory anthropic principle dares to ask if consciousness itself is not just a product of the universe, but a fundamental ingredient in its creation. In this radical view, the quantum fluctuations we have explored are more than just random jitters. They are the raw material of reality, waiting for a conscious mind to give them definite form. The core quantum mystery this theory tackles is the measurement problem. In the strange rules of the quantum world, a particle does not have a definite position or state until it is measured. It exists in a blur of all possible states at once, a condition known as a superposition. The moment an observation is made, this cloud of potential collapses into a single, concrete reality. The question that has haunted physicists for a century is, what exactly counts as a measurement? Is it the interaction with a laboratory instrument, or does it require something more, something with awareness? The participatory anthropic principle suggests the latter. It proposes that the universe only becomes real and definite when it is observed by a conscious being. The quantum fluctuations permeating the vacuum are the endless possibilities, the unwritten scores of reality, and consciousness is the conductor that forces one melody to emerge from the noise. This leads to a stunning implication for the cosmos itself. In the early universe, before the first stars ignited and the first life forms evolved, there were no conscious observers. According to this idea, the entire cosmos would have existed in a state of global superposition. It was not one specific universe, but a shimmering potential of all possible universes at once, a cosmic wave function of unimaginable breadth. The quantum fluctuations imprinted in the cosmic microwave background, the very seeds of galaxies, were not mere accidents. They were the first tremors of actualization, the points where potential began to crystallize into the specific reality we now inhabit. They were the universe beginning to observe itself. This is not to say a human mind magically reached back in time. Instead, the principle implies that consciousness is a fundamental property woven into the fabric of existence, and its eventual emergence was enough to retroactively solidify the past that made it possible. We are not just living in a universe suited for life. Our act of observation is what helps to continually create and define it, tying our own existence inextricably to the very nature of reality. This cosmic fragility points toward an unsettling possibility. Our universe may be living on borrowed time, perched precariously in a state of temporary peace. This is the theory of vacuum decay, and it hinges on a simple but terrifying question: what if our vacuum is not truly empty? What if it is only almost empty, a state physicists call a false vacuum? Imagine a vast, tranquil valley nestled high in the mountains. This valley is not the true lowest point, however. A deeper, more stable valley lies far below, separated by a massive, fragile mountain pass. Our universe is like a ball resting peacefully in the upper valley. It seems stable, and for all practical purposes, it is, but it is not in its ultimate, lowest energy state. It is trapped in a false minimum, a cosmic comfort zone that could, at any moment, collapse. The mountain pass holding us in this false vacuum is not made of rock, but of quantum fields, primarily the Higgs field that gives particles their mass. The stability of our entire reality depends on the precise shape of this field's energy landscape. A large enough quantum fluctuation could provide the kick needed to push a tiny region of space over that energy barrier and into the true vacuum below. This would be the trigger for a cosmic catastrophe unlike any other. In that instant, a bubble of true vacuum would form. Its wall would be a sphere of fundamental change, a rewriting of physics itself, expanding in all directions at the speed of light. Inside this bubble, the laws of nature as we know them would cease to exist. The Higgs field would settle into a new value, which would instantly alter the properties of every fundamental particle. Atoms could no longer hold their structure. The very forces that bind matter together would unravel. Everything the bubble touched, every planet, every star, every molecule, would simply dissolve into a new, alien state of being. There would be no warning, no sound, no flash of light. One moment, reality is as it has always been. The next, an invisible sphere of total transformation is upon you. and then nothing you would recognize as existence remains. This is not science fiction, it is a legitimate, though statistically remote, prediction derived from our best models of particle physics. The fact that the universe has lasted for billions of years suggests our false vacuum is exceptionally stable. But the haunting implication is that the quantum fluctuations that gave birth to our cosmos could also be the instrument of its ultimate end. This profound connection between particles hints at a secret architecture woven into reality itself. A revolutionary idea, known as the ER=EPR conjecture, dares to propose that the spooky link of quantum entanglement is not a ghostly, non-physical connection at all. Instead, it suggests that every pair of entangled particles is secretly joined by a microscopic wormhole. The EPR part of the name comes from a famous thought experiment by Einstein, Podolsky, and Rosen, who used quantum entanglement to argue that the theory was incomplete, famously calling it spooky action at a distance. The ER refers to the Einstein-Rosen bridge, the formal name for a wormhole, a tunnel through the fabric of spacetime. This conjecture boldly claims they are two different descriptions of the same fundamental phenomenon. Imagine two electrons born together, their fates forever linked. If one spins up, the other instantly spins down, no matter how far apart they travel. According to this theory, their instantaneous connection is not magic, it is geometry. A tiny Planck-scale wormhole, far too small for any matter or light to ever traverse, connects them. This wormhole does not provide a shortcut for travel, but it does provide a physical, geometric explanation for their mysterious correlation. The quantum fluctuations in the vacuum could then be seen as the faint, residual tremors from this hidden network of tunnels, the constant activity of spacetime stitching itself together at the smallest possible scales. This idea emerged from the fiery intersection of black hole physics and quantum information theory. Scientists realized that the quantum entanglement between particles leaking out of a black hole as Hawking radiation and particles that fell inside could be described by the geometry of a wormhole connecting them. This provided a stunningly elegant potential resolution to the black hole information paradox. The information is not lost or just scrambled in the radiation, it is preserved by traveling through the wormhole that entanglement creates. This suggests that spacetime is not a fundamental stage, it is an emergent structure, a dynamic fabric woven from countless threads of quantum entanglement. Every quantum connection, every spooky handshake between particles, is literally a stitch in the tapestry of space and time. The universe we perceive as vast and three-dimensional may be the holographic projection of a vast, interconnected quantum network, with the quantum fluctuations we detect being the hum of its endless weaving. This hidden architecture of entangled tunnels in emergent space leads to a startling question: what if the universe is not a fundamental reality at all, but a construct? The simulation hypothesis takes the strange rules of quantum mechanics and reads them as potential source code. In this view, the seemingly random nature of quantum fluctuations is not a feature of deep reality, but a design element of an incredibly advanced simulation. True randomness is notoriously difficult to generate, even for an ultra-powerful computer. It requires a source of genuine entropy, a complex and resource-intensive process. For a simulation modeling an entire universe, determining the outcome of every single quantum event with perfect precision would demand unimaginable processing power. Instead, the simulation could use a more efficient method, probabilistic outcomes. When a quantum particle has to choose a path, the simulation does not calculate a single, predetermined result. It simply rolls a digital die, allowing the particle to behave according to a set of probabilities. The quantum jitter we measure would then be the outcome of these efficient, pseudo-random number generators built into the fabric of the simulation itself. This would make the universe computationally tractable, a manageable program rather than an infinitely complex calculation. The quirks of quantum physics begin to look less like mysterious laws and more like optimized software protocols. Consider the famous double-slit experiment. When you are not watching, a particle behaves like a wave, passing through both slits at once and creating an interference pattern. The moment you set up a detector to observe which slit it goes through, the particle collapses into a definite object and the wave pattern vanishes. This is eerily similar to how a video game engine works. A modern game does not render every leaf on every tree in a vast forest all the time that would melt the processor. Instead, it uses a technique called level of detail. Only the parts of the world that a player is actually looking at are rendered in high definition. Everything else exists as a low-resolution placeholder or simple data. The act of observation of looking triggers the rendering process. In the quantum world, the act of measurement could be the trigger that forces the simulation to fully render a specific outcome, to collapse the wave function and decide, for instance, which slit the particle actually went through. Until then, it remains in an unrendered, probabilistic state to save on computational resources. From this perspective, quantum fluctuations are not glitches, but the background noise of the simulation's central processing unit. They are the hum of the cosmic computer, the slight imperfections in its random number generators, or even intentional features designed to create the texture of a believable, unpredictable reality. This idea blends the hardest edges of physics with the deepest questions of philosophy, forcing us to wonder if the fundamental grain of our existence is not Planck length, but pixel. If spacetime is a fabric, then perhaps we have been looking at the wrong side of the cloth. Loop quantum gravity proposes that the smooth, continuous stage of Einstein's universe is an illusion, a grand average of a reality woven from a billion tiny, indivisible stitches. This theory suggests that space itself is not infinitely divisible. It comes in discrete, fundamental units, tiny loops of gravity's field, one-dimensional threads of pure geometry. These loops are the atoms of space, and they cannot be cut or divided any further. They link together, weaving a dynamic, evolving network known as a spin network. Picture a cosmic tapestry of interconnected rings, a vast, shimmering web where each intersection or node represents a tiny grain of volume, and each link represents a quantum of area. The familiar three-dimensional space of our everyday life emerges from the complex connections of this underlying network, much like a smooth, solid piece of fabric emerges from the intricate weaving of individual threads. So, what are the quantum fluctuations that permeate the vacuum in this picture? They are not just particles flickering in and out of an empty void, they are the vibrations of the fabric itself. Each tiny loop in the spin network can be excited, humming with energy like a plucked guitar string. These vibrations are the most fundamental particles, the quanta of matter and force, emerging directly from the music of spacetime. A fluctuation is a note played on the cosmic lattice, a tiny change in the network structure that we perceive as a particle or a field. This radical rethinking of reality's foundation has a profound consequence for the universe's most dramatic events. In Einstein's general relativity, black holes contain a point of infinite density called a singularity, and the Big Bang began from such a point, but infinity is a sign that a theory has broken down. Loop quantum gravity removes these singularities entirely. Because space is quantized, it cannot be compressed into an infinitely small point. There is a smallest possible volume. When matter collapses under its own gravity, it reaches this maximum possible density and then rebounds. This leads to the stunning idea of a big bounce. Our universe may not have been born from a single, explosive point of nothingness. Instead, It could be the latest cycle in an eternal cosmic rhythm, a great rebound from a previous universe that collapsed into a hot, dense state before reaching the fundamental limit and springing back into a new expansion. The quantum fluctuations that seeded our galaxies might be the faint, residual echoes of that primordial bounce, the vibrations of spacetime itself ringing out from the dawn of time. This branching reality offers a breathtakingly simple, yet dizzying, answer to the quantum riddle. The many worlds interpretation dismisses the idea of random collapse entirely. It proposes that every time a quantum system faces a choice, the universe does not choose. Instead, it bifurcates. Every single possible outcome is realized, but each in its own newly formed, perfectly real branch of reality. Think of the vacuum's quantum fluctuations, those pairs of virtual particles flickering in and out of existence. In our world, we might measure one specific outcome for a fleeting instant. But according to many worlds, at the very moment of that fluctuation, the cosmos split. In one branch, the particle pair appeared exactly as we detected it. In another, equally real branch, it did not appear at all, and in countless others, it appeared with slightly different energies or trajectories. There is no single, random dice roll. There is only a continuous, unending forking of paths, a cosmic tree of possibilities growing new limbs with every quantum tremor. This interpretation is radically deterministic. Nothing is ever truly left to chance. The entire evolution of the universe is governed by the strict, unwavering equations of quantum mechanics. The probability we calculate for an event is not the odds of it happening, but a measure of how many branches of the multiverse will contain that particular outcome. From our limited perspective, trapped on a single branch, it feels like randomness, but from a God's eye view, every possibility is fulfilled somewhere. This has a profound implication for you, the observer. Every decision you have ever made, from the monumental to the mundane, was preceded by quantum events in your brain. According to many worlds, each of those tiny fluctuations caused a split. This means there is a branch of the multiverse where you took a different route to work this morning. Another where you chose a different career. Another where an entirely different set of quantum fluctuations during the Big Bang led to a universe without stars, and a version of you, or something like you, exists there to witness it. The version of you listening to this now is just one thread in an infinite tapestry of selves, each living out a different variation of a life, all equally valid. The quantum fluctuations we measure in our experiments are not fundamental randomness. They are merely the particular tremor that resonates along our specific branch of the cosmic tree, while an infinite chorus of other tremors echoes through the rest of the forest. Perhaps the strangest aspect of quantum mechanics is its inherent randomness, a fundamental fuzziness we are told we must simply accept, but what if we do not have to? A bold alternative known as stochastic electrodynamics, or SED, challenges the very core of quantum orthodoxy. It dares to suggest that the quantum world is not fundamentally probabilistic at all, but is instead a classical system driven by a hidden engine, the zero-point field we have already met. In this view, the famous uncertainty principle is not a statement about the limits of knowledge. It is a statement about the physical reality of a particle being constantly buffeted by an all-pervasive sea of energy. A tiny particle, like an electron, is not a fuzzy cloud of probability. It is a definite object with a real position and momentum, but it exists in a state of perpetual tremor, jostled and shaken by the relentless, random fluctuations of the zero-point field. Its path is not uncertain because of a mysterious quantum law, but because it is constantly being pushed around by this invisible storm. This offers a profoundly different, and, for many, a more intuitive, picture of reality. The bizarre behavior of particles in the double-slit experiment, where they seem to act as waves, finds a causal explanation in SED. The particle is still a particle, taking one definite path through one slit. But on its journey, it is constantly interacting with the zero-point field. This interaction pushes and pulls on the particle, subtly altering its trajectory. When many such particles are fired, their paths are collectively shaped by the field's fluctuations, building up the famous interference pattern one impact at a time. The pattern emerges not from a wave of probability, but from the statistical outcome of countless classical particles being guided by a random background force. This theory manages to reproduce many of the precise results of standard quantum mechanics without ever invoking a wave, function, or a probability amplitude. It reframes the quantum world from a realm of inherent mystery into a deterministic, if chaotic, classical system. The quantum fluctuations are no longer a fundamental puzzle. They are the classical driving force behind every quantum phenomenon, the hidden hand that guides the dance of the very small. These hidden patterns in the quantum world hint at a geometry so profound it could render our most basic concepts obsolete. A radical new formulation known as the amplituhedron suggests that spacetime itself, along with the quantum fluctuations that fill it, might be a side effect, a mere echo of a much deeper and more perfect geometric reality. The amplituhedron is a multi-faceted geometric object, like a jewel existing in an abstract, higher-dimensional space. Its volume directly encodes the outcomes of particle collisions, the so-called scattering amplitudes that physicists work so hard to calculate. The truly revolutionary part is how it achieves this. In traditional quantum field theory, calculating what happens when particles collide is an immensely complex chore. You must account for every possible path a particle could take, every possible quantum fluctuation in the vacuum, and every possible exchange of virtual particles. It is a messy, complicated process rooted in our familiar concepts of space, time, and causality. The amplituhedron bypasses all of that. It calculates the exact same probabilities for particle interactions without any reference to space, time, or even quantum uncertainty. Locality, the idea that objects are influenced directly only by their immediate surroundings, is a cornerstone of our physics. Unitarity, the principle that probabilities must always add up to 1, is another. Yet the amplituhedron shows that these fundamental features of our universe are not primary. They emerge from its perfect geometry. The quantum fluctuations we perceive as the restless energy of the vacuum could simply be the shadows cast by this object as it turns in its higher dimensional space. This is like discovering that the entire intricate plot of a novel is actually just the projection of a single, elegant equation. The seemingly random, probabilistic dance of the quantum world is not random at all. It is the inevitable consequence of a sublime and rigid geometric form. The amplituhedron points toward a future physics where the universe is not built on quantum fields vibrating in spacetime, but on a timeless, spaceless, and breathtakingly beautiful mathematical truth. This hidden lattice of spacetime could transform the darkest objects in the cosmos from cosmic trash compactors into radiant stellar corpses. We call them Planck stars. Within the framework of loop quantum gravity, the terrifying singularity at the heart of a black hole, that point of infinite density, simply cannot exist. Space itself has a smallest possible grain, a fundamental pixel size. As a dying star collapses into a black hole, its matter is crushed to unimaginable densities, but it cannot reach infinity. Instead, it compresses to the absolute maximum allowed by the quantum structure of space. At this extreme, the quantum fluctuations of the gravitational field itself, the vibrations of the spacetime fabric, become overwhelmingly powerful. These are not fluctuations of particles in space, but fluctuations of space. They generate a tremendous repulsive force, a quantum gravitational pressure that acts like a cosmic spring. The collapse does not end in a singularity. It halts, rebounding to form a stable, ultra-dense object, a Planck star, suspended just beyond its own event horizon. This stellar core is smaller than an atom, yet it contains the mass of a star, frozen in a state of ultimate density. This single idea elegantly sidesteps the information paradox. Since there is no singularity to act as a cosmic shredder, the information about everything that falls into the black hole is never truly destroyed. It is imprinted onto the surface of this tiny, dense Planck star, preserved rather than erased. So what of Hawking radiation? In this picture, the slow leak of energy from a black hole is not just a quantum trick at the event horizon. It is the slow evaporation, the quantum tunneling, of the Planck star itself. Over eons, the star loses mass and energy, shrinking until it eventually vanishes, releasing all the stored information back into the universe. The black hole does not end with a paradox, but with a final flash of light containing the complete history of everything it ever consumed. The ghostly hum of quantum gravity provides both the pressure to create these stellar fossils and the mechanism for their eventual, informative demise. This elegant solution, however, ignited a new and ferocious conflict. The black hole firewall paradox is a modern crisis that threatens to tear physics apart at the seams, and it all comes down to a single, devastating question about what happens at the edge of a black hole. To understand it, we must follow the life of a pair of entangled particles created by a quantum fluctuation just outside the event horizon. One particle falls in, while its entangled partner escapes as Hawking radiation. Now consider the fate of the black hole over eons. As it evaporates, the escaped Hawking particles must remain entangled with the particles that fell in long ago, preserving the information. But here lies the terrible snag. Quantum mechanics has a strict rule, the monogamy of entanglement. A particle can be fully entangled with only one partner at a time. The escaping particle is entangled with its original partner inside the black hole, yet, for the information to be preserved in the outgoing radiation, that same escaping particle must also become entangled with the Hawking radiation that left before it. It cannot be entangled with both. To resolve this, physicists found a grim solution. The entanglement between the particle inside and the one outside must be violently severed. The energy released by breaking this profound quantum link would manifest as an inconceivably intense wall of energy, a firewall of ultra-high energy particles, right at the event horizon. This is not a gentle glow. It is a searing boundary of pure fire that would incinerate anything crossing it. This is where Einstein's universe shatters. The cornerstone of general relativity is the equivalence principle, which states that falling through an event horizon should be an uneventful experience. If you were falling into a stellar mass black hole, you would feel nothing special as you crossed that invisible boundary. Spacetime should be smooth. The firewall makes a mockery of this. It places a tangible, destructive structure at a location that should be empty space, fundamentally violating our understanding of gravity. So we are left with an impossible choice. Either quantum mechanics is correct and a lethal firewall exists, burning everything to a crisp, or general relativity is correct and the horizon is smooth and safe, but then quantum information is lost forever, breaking quantum theory. There is no comfortable middle ground. Quantum fluctuations, the very mechanism that creates Hawking radiation, have set a trap for our most fundamental theories, forcing them into a duel to the death at the edge of reality. This cosmic firewall presents an impossible choice. but perhaps the universe has a deeper law that forbids such paradoxes from ever arising. Stephen Hawking proposed a safeguard known as the chronology protection conjecture, a theory that the laws of physics actively prevent time travel to the past. The equations of general relativity do, in fact, permit the theoretical construction of a time machine. Certain extreme configurations of matter and energy, like an infinitely long, rotating cylinder or the interior of a specific type of wormhole, could create what physicists call a closed time-like curve. This is a path through spacetime that loops back on itself, allowing you to travel into your own past, yet we see no time tourists from the future. Hawking argued that this is not a coincidence. He suspected that whenever such a structure is on the verge of forming, quantum effects would intervene to destroy it. The mechanism for this cosmic sabotage is the relentless activity of the quantum vacuum. Imagine a closed time-like curve beginning to form. A single virtual particle pair flickers into existence near this nascent time loop. One particle could travel along the loop, going backward in time, and interact with its own earlier self in a way that amplifies its energy. This particle then completes the loop, traveling back again, interacting with its past self once more, and getting even stronger. This cycle would repeat over and over, with the same particle building up its own energy in a runaway feedback loop. The quantum fluctuation would not just be a tiny jitter, it would become an avalanche. The energy density in the region of the time machine would skyrocket toward infinity, creating a catastrophic instability. The sheer buildup of this quantum energy would either destroy the time machine itself or warp spacetime so severely that the closed time-like curve could never be completed. In this view, quantum fluctuations act as the universe's ultimate paradox police. They are not random background noise, they are a fundamental stabilizing force, ensuring that cause always precedes effect, that history remains coherent and singular. The reason you cannot go back and prevent your own birth is not a philosophical constraint. It is woven directly into the seething, protective nature of the vacuum itself, guarding the chronology of reality from its own potential contradictions. The Higgs boson is a cosmic tightrope walker, balancing the entire structure of matter on its back, but according to our best calculations, this balance should be impossible. This is the hierarchy problem, a deep crisis in physics that quantum fluctuations created. The mass of the Higgs particle is not just a number, it is a fundamental property that determines how all other particles get their mass. The problem is that the Higgs exists in the seething quantum vacuum, constantly bombarded by virtual particles flickering in and out of existence. Every single one of these fleeting interactions contributes a little kick to the Higgs, like a crowd of invisible hands constantly pushing it. The combined effect of all these quantum corrections from every type of particle should drive the Higgs mass to an astronomically high value, up to the Planck scale. This would make it 100 million billion times heavier than it actually is. If that were true, the delicate balance of forces that allows atoms to form would be shattered. Stars would never ignite, and the universe would be a barren, lifeless void, yet we exist. The Higgs mass is curiously, perfectly light, so what tames these wild quantum fluctuations? One elegant solution proposes a hidden symmetry woven into the fabric of reality, a symmetry so profound it doubles the number of elementary particles. This is supersymmetry, or SUSY. The theory posits that for every known particle we have discovered, from electrons to quarks, there exists a hidden superpartner. The electron has a selectron, the quark has a squark, the photon has a photino. These are not mere duplicates, they are a shadow population that stabilizes the cosmos. The magic happens in the quantum accounting. Remember those virtual particles giving the Higgs mass-kicking pushes. In a supersymmetric universe, For every push from a standard particle, its superpartner delivers an equal and opposite pull. The quantum fluctuations of a particle and its partner are perfectly matched in magnitude, but opposite in sign. Their contributions to the Higgs mass cancel each other out with exquisite precision, leaving the Higgs naturally light and stable. The hierarchy problem simply vanishes, resolved by a beautiful, hidden symmetry. The hunt for this symmetry is one of the grandest quests in modern science. At the Large Hadron Collider, physicists are smashing protons together at unimaginable energies, searching for the faintest trace of a selectron or a photino. They have not found them yet, at least not in the form they expected. This absence is a profound puzzle. If supersymmetry is real, why have we not seen these partners? Perhaps they are simply heavier than our current machines can produce, hiding just beyond our reach, or perhaps the symmetry is broken in a subtle way, meaning the cancellation is not perfect, but just good enough to leave the tiny wisp of mass we observe. Finding a superpartner would be more than just discovering a new particle. It would be our first direct evidence of a cosmic balancing act, a glimpse into the hidden mechanism that keeps the quantum chaos in check and makes our material world possible. This paradox, born from Hawking's own work, has forced physicists to tear down and rebuild our understanding of reality. The core conflict is stark. Quantum mechanics insists that information is indestructible. It can be scrambled beyond recognition, like a book burned to ashes, but never truly erased from the cosmic ledger. Yet Hawking's original calculation showed a black hole evaporating into a featureless, random glow of heat, seemingly carrying no details of the stars, planets, or books it consumed. This presented an impossible choice. Either our most successful theory of the very small is fundamentally wrong, or our understanding of gravity is incomplete. The resolution likely lies in the quantum fluctuations themselves and the strange role of entanglement. Modern thought suggests the information is not destroyed, but undergoes an extreme transformation. As matter falls toward the event horizon, its information is scrambled by the intense gravitational field and the chaotic quantum jitters at the boundary. It is like throwing a complex mosaic into a turbulent, high-energy blender. The individual tiles are shattered and mixed, but they are not annihilated. This scrambled information then becomes imprinted onto the Hawking radiation that escapes, not in any simple, readable order, but encoded within the intricate pattern of the radiation itself. Decoding it would be a task of almost unimaginable complexity, like reconstructing a burned book from the precise dance of the rising smoke and the distribution of heat in the ashes. This idea connects deeply to the holographic principle. The information describing everything within the black hole's volume is not stored inside, but is encoded on its two-dimensional surface, the event horizon. The Hawking radiation, which originates from quantum fluctuations at this horizon, carries that information away as the black hole shrinks. An even more radical idea to resolve the paradox is the concept of entanglement islands. Imagine a region just inside the event horizon, a secret island that is not completely cut off from the outside world. Due to the bizarre properties of quantum entanglement, this interior island is, in a gravitational sense, also part of the exterior. The information that fell in is not lost deep in the singularity. It is stored on this island, which remains subtly connected to the escaping radiation through a web of quantum links. As the black hole evaporates, this island effectively moves outward, and its stored information is gradually transferred to the Hawking radiation, ensuring nothing is ever truly lost. These modern resolutions paint a picture where quantum fluctuations are not just random noise, they are the active agents of information processing, scrambling and transferring the cosmic ledger in a way that preserves the most sacred rule of quantum physics, even in the face of a gravitational abyss. This very entanglement that connects particles may be the true source of space itself. We are exploring a breathtaking idea that spacetime is not a fundamental stage, but an emergent phenomenon, a collective illusion born from a vast cosmic web of quantum connections. This is the it from qubit paradigm, where reality's fundamental ingredients are not tiny points of matter, but bits of quantum information and their intricate correlations. In this view, the universe is not made of stuff, it is made of relationships. The quantum fluctuations we have been exploring are not tremors in space, they are the microscopic dynamics of this underlying network, the constant flickering of entanglement links being forged and broken. To understand how this works, we need a new measure, entanglement entropy. This is not the familiar chaos of thermodynamics, but a precise measure of the quantum information shared between two systems. When two particles are perfectly entangled, their entanglement entropy is high, meaning their fates are deeply intertwined. When they are separate, their entropy is low. The stunning revelation is that this quantum measure of connection behaves exactly like gravity. For a region of space, the entanglement entropy between what is inside and what is outside is not proportional to the volume of the region, as you might expect. It is proportional to the area of its boundary. This is a direct echo of black hole physics, where a black hole's entropy, its information content, is also tied to the surface area of its event horizon, not the volume within. This is a profound clue that space and gravity are deeply rooted in quantum information. Imagine space as a magnificent tapestry. From a distance, it looks like a smooth, continuous fabric. But if you bring your eye right up to it, you see it is woven from countless individual threads. Each thread is a quantum connection, a bond of entanglement between two quantum bits or qubits. The smooth geometry of Einstein's general relativity is the large-scale pattern of this weaving. The gentle curve of a planet's orbit is the cumulative effect of billions upon billions of these threads pulling together in a coherent pattern. And the quantum fluctuations, they are the individual threads trembling, snapping, and re-knotting. They are the tiny, constant changes in the entanglement patterns that make up the fabric of reality. When a virtual particle pair flickers at the edge of a black hole, it is not happening in space, it is a fundamental rewiring of the cosmic network, a change in the entanglement that actually defines that region of space. The fluctuation is the process itself. This means the empty space around you is not passive nothingness, it is a seething, dynamic network of quantum links, and what you perceive as a gentle hum of energy is the sound of the universe constantly stitching itself together, one entangled connection at a time. If the universe is a tapestry woven from quantum information, then time might be its most intricate illusion. The Wheeler-DeWitt equation stands as one of the most profound and puzzling results in theoretical physics. It represents an attempt to apply the rules of quantum mechanics to the entire cosmos, describing the universe with a single, stationary wave function. Yet this equation contains a shocking omission. There is no time variable. In this fundamental description of reality, time simply does not appear. This is the notorious problem of time. The equation suggests that the universe, at its most basic level, is static and frozen. The relentless flow of time we feel in our bones, the progression from past to present to future, cannot be a fundamental feature. It must be an emergent property, a story that unfolds from a deeper, timeless reality. In this picture, the quantum fluctuations we have explored are not events that happen in time. They are timeless variations in the possible configurations of the universe, like the different, frozen frames of a movie reel, all existing at once. So how does the movie start playing? How does time emerge from this timeless foundation? One compelling idea points to a cosmic clock. If one component of the universe, perhaps a dominant field or a uniform cloud of matter, changes in a smooth and predictable way, the rest of the universe can use that change as a reference. Your experience of time passing could be the result of comparing the ever-changing state of your brain to this slow, cosmic tick. Another, even more fascinating proposal is that time itself emerges from quantum entanglement. Remember the idea that space is woven from entangled connections. Time may be the direct result of the way these connections change. When two quantum systems become entangled, the correlation between them creates a sequence, a before and after. The continuous process of subsystems entangling and disentangling within the universal wave function generates the ordered progression we perceive as the flow of time. From this radical perspective, the quantum fluctuations of the vacuum are not tiny tremors in the fabric of spacetime. They are the timeless, fundamental entities whose shifting relationships and correlations actively construct the stage of time upon which our lives play out. The ticking of your watch is just the echo of a deeper, quantum rhythm. This formula, scribbled on a blackboard, reveals a universe built from information. The Bekenstein-Hawking entropy tells us that a black hole's information content is not proportional to the immense volume it contains, but to the surface area of its event horizon. The larger the black hole's surface area, the more entropy it has. This was a staggering departure from everything we knew, where entropy always scales with volume. It was a direct hint that our reality is not what it seems. If entropy is a measure of the number of ways a system can be arranged on the microscopic level, then a black hole's entropy counts the number of its possible internal configurations. The Bekenstein-Hawking formula gives us that precise number. It tells us that the total information a black hole can hold is exactly 1/4 of the area of its event horizon, measured in tiny squares of the Planck area. This points to a breathtaking conclusion. The surface of a black hole must be tiled with fundamental, indivisible units of area, each one a single pixel in the cosmic display. Each of these Planck area pixels can be thought of as a single bit of information, a switch that can be either on or off. The quantum fluctuations we detect at the event horizon, the frenetic dance of virtual particles, are not random noise. They are the physical manifestation of these microscopic switches' changing state. Every flicker of a virtual pair is a bit flip on the horizon surface, a single pixel in the vast screen updating its information. This ties gravity, thermodynamics, and quantum mechanics into a single, elegant knot. The temperature of a black hole, its Hawking radiation, and its immense entropy all emerge from the statistical behavior of these countless quantum microstates on its boundary. The event horizon is not a smooth, featureless membrane. It is a dynamic, shimmering mosaic of quantum information, and its gentle hum is the sound of the universe processing data. This granularity is not limited to black holes. It implies that all of spacetime has a fundamental pixelated structure. The smooth, continuous space of our everyday experience is an illusion, a grand average of a reality built from countless tiny, vibrating bits. The quantum foam, the seething vacuum fluctuations that permeate the cosmos, are the result of this underlying grid of information constantly processing, updating, and reconfiguring itself. We are living inside a computational matrix whose resolution is the Planck length. Even the fabric of cause and effect might be woven from something more fundamental. Causal set theory offers a starkly elegant vision, proposing that spacetime is not a smooth, continuous stage, but a vast, discrete collection of events. Each event is a single point, a moment of happening, and these points are connected in a network defined solely by a partial order of causality. One event either causes another, or it does not. This cosmic web of cause and effect relationships is the true bedrock of reality. with our familiar four-dimensional universe emerging as a large-scale approximation. The smooth continuum described by Einstein is an illusion, a statistical average of this underlying, grainy network of causal links. In this picture, the relentless quantum fluctuations of the vacuum take on a new and specific role. They are the random sprinkling of new events into the growing causal set. With each fluctuation, a new point of cause or effect is added to the network at random, expanding the tapestry of reality one causal connection at a time. The universe is not expanding into a pre-existing void, it is actively growing by accumulating these fundamental events. This process naturally incorporates the holographic principle, as the information content of a region is bound by the number of these causal links on its boundary, not the volume within. The theory ambitiously aims to explain why our universe appears to obey Lorentz invariance, the principle that the laws of physics are the same for all observers moving at constant velocity. From the chaotic, random sprinkling of new events, the large-scale symmetry of spacetime miraculously emerges. It also offers a fresh path to tackling the cosmological constant problem. The value of dark energy could be a direct consequence of the rate at which new events are being added to the causal set, a fundamental parameter of the universe's growth. The premise is beautifully simple, yet its implications are profound. The universe is not a container where things happen. It is the happening itself, a growing network of relationships, and the quantum jitter we detect is the sound of new causes being born into existence. Our most basic intuition about space is about to be appended. We imagine a location as a simple set of coordinates, a dot on a map defined by its street and avenue. In our world, it does not matter if you note the avenue first or the street first, the location remains the same, the order of your measurement is irrelevant. But at the universe's most fundamental scale, this simple commutativity breaks down. In the theory of non-commutative geometry, the very coordinates of spacetime refuse to follow this familiar rule. The act of measuring position in one direction fundamentally interferes with measuring position in another. The sequence of your observations matters, creating an inherent, unresolvable fuzziness in the fabric of reality itself. This is not a blurriness of our instruments, but a fundamental property of a quantum spacetime. It is the Heisenberg uncertainty principle woven directly into the geometry of the cosmos. You cannot simultaneously pin down reality's exact coordinates because those coordinates are not independent numbers on a grid, they are dynamic, interlocking operators in a vast, cosmic algebra. Their refusal to commute, their insistence that x times y is not the same as y times x, builds uncertainty directly into the architecture of existence. What we perceive from our macroscopic vantage point as the gentle hum of quantum fluctuations, the flickering of virtual particles in the void, is the macroscopic echo of this deep, geometric fuzziness. The vacuum is not perfectly still because spacetime itself is fundamentally uncertain, a seething foam of non-commutative coordinates. This elegant mathematical framework does more than just explain the jitter, it offers a profound gift to theoretical physics. It naturally smooths away the terrifying singularities predicted by general relativity. In Einstein's theory, black holes contain a point of infinite density, and the Big Bang began from such a point, places where the smooth fabric of spacetime tears and the laws of physics break down. But in a non-commutative geometry, you can never localize a point with infinite precision. The fundamental fuzziness prevents any quantity from reaching a true mathematical infinity. The singularity is replaced by a smeared, fuzzy region of extreme, but finite, density. The universe avoids its own self-destruction not through a mysterious new law, but through the innate blurriness of its own constituent geometry. In this view, the quantum fluctuations are not particles popping in and out of a pre-existing space. They are the space, the very manifestation of a reality whose coordinates are in a constant, irreducible dance of uncertainty. This dizzying paradox forces us to accept a reality that is fundamentally divided. The black hole complementarity principle offers a radical escape from the firewall dilemma by declaring that both conflicting stories are true. For an astronaut floating safely outside the event horizon, the story is one of preservation. From this external viewpoint, all the information about anything that falls into the black hole never actually crosses the boundary. Instead, it is scrambled and smeared across the event horizon itself, a holographic film clinging to the surface. The quantum fluctuations at this boundary are not creating random thermal radiation. They are actively encoding and transmitting this smeared information, bit by bit, into the outgoing Hawking radiation. The information is never lost, it is meticulously, if chaotically, released back into the universe. Yet, for another astronaut bravely falling into the same black hole, the story is entirely different. According to their direct experience, the event horizon is not a fiery wall or a sticky membrane. It is completely invisible and uneventful. They pass smoothly through it, following the gentle curve of spacetime described by Einstein, with no sudden fire or tearing of atoms. Both of these accounts, the external story of information smearing and the internal story of smooth passage, are simultaneously correct. They are complementary descriptions of the same physical reality, valid only within their own frames of reference. The principle forbids any single observer from ever seeing a contradiction. The outside observer can only watch the information slowly leak out from the horizon, while the infalling observer simply falls in, with no way to send a message back out that would violate the external description. This solution rests entirely on the frame-dependent nature of reality itself. The quantum fluctuations at the horizon are not an objective, singular phenomenon. What one observer measures as a gentle, information-carrying glow is, for the other, a featureless vacuum. The very act of measurement, of defining a particle or a fluctuation, is tied to the observer's own motion through the cosmos. This pushes the inherent weirdness of quantum mechanics, where observation defines reality, to its most extreme possible environment. It suggests that in the face of a gravitational monster, the universe simply refuses to pick a single truth, operating instead with a divided consciousness that ensures its own logical consistency, no matter the perspective. The relentless tick of your clock might be the universe cooling down. This is the startling claim of the thermal time hypothesis, a theory that reimagines time not as a fundamental river flowing through the cosmos, but as a ghost, an emergent property born from a cosmic temperature difference. In this view, the flow of time is an illusion generated by a statistical process, the universe's slow, inevitable march from a hot, ordered state toward a cold, disordered equilibrium. What we experience as the unstoppable progression from past to future is simply our perspective on this grand thermal gradient. Think of a steaming cup of coffee sitting in a cool room. The heat from the coffee flows into the room, and this irreversible process defines a clear arrow of time for the coffee. You would be shocked to see the coffee spontaneously draw heat back from the room and get hotter. That process defines a before and an after. Now, imagine the entire cosmos as that cup of coffee, still holding the fading warmth of the Big Bang, radiating its heat into the ultimate cold of deep space. Our perception of time is our experience of riding this cosmic cooling trend. So, where do quantum fluctuations fit into this thermal story? They are the microscopic engines of this temporal flow. Each tiny jitter in the vacuum, each virtual particle pair flickering into existence, is a small, random step in the universe's statistical dance toward maximum entropy or disorder. These fluctuations are the individual molecular collisions that, on a vast scale, drive the heat to flow from hot to cold. In a hypothetical universe that had already reached perfect thermal equilibrium, a state of maximum entropy, there would be no net flow of energy, no temperature differences, and thus no perceived direction of time. The quantum fluctuations would still occur, but they would be perfectly symmetric with no overall trend. An observer in such a timeless, equilibrium cosmos would see events that appear to run forward and backward with equal probability. The very concepts of cause and effect would lose their meaning. This leads to a profound connection with our cosmic origins. The reason we have a strong arrow of time at all is because our universe began in a state of incredibly low entropy, a highly ordered and specific configuration at the moment of the Big Bang. It was like a pristine, unshuffled deck of cards. The quantum fluctuations that were imprinted on the cosmos during its inflationary phase were the first tiny shuffles, initiating the process that would eventually lead to the formation of galaxies, stars, and planets. They set the universe on its one-way journey toward disorder. From this perspective, every second that passes is a measure of the universe forgetting its initial, highly ordered state, and the quantum hum of the vacuum is the sound of that forgetting in progress. Your own consciousness, processing memories of the past and anticipation of the future, may be the most intricate expression of this cosmic thermal gradient, a fleeting pattern sustained by the universe's long, slow descent into equilibrium. This grand tapestry of possibilities finds its most ambitious expression in a single, elegant idea. String theory dares to be the final theory, a framework that unites the quantum world with the cosmic stage of gravity. It proposes a breathtakingly simple shift in our understanding of reality's building blocks. Forget point-like particles. The true fundamentals of the universe are unimaginably tiny, vibrating loops of energy. Think of these strings as the universe's most fundamental instruments. A violin string can vibrate in different modes to produce a cello's deep note or a flute's high pitch. In exactly the same way, a single fundamental string can vibrate at one frequency to become an electron, and at another frequency to become a quark or a photon. Every particle we have ever discovered, every force carrier, is just a different resonant note played on this cosmic string. This single concept elegantly incorporates gravity. The graviton, the hypothetical particle that carries the gravitational force, emerges naturally as another vibration in the string's repertoire. For the first time, a theory promises to describe all of nature's forces and particles under one roof, woven from the same vibrating fabric. But this beautiful unity comes with a staggering implication, a concept known as the string theory landscape. The mathematics of string theory does not point to one unique universe with our specific laws of physics. Instead, it describes a colossal landscape of possibilities, a vast collection of perhaps 10 to the 500 different stable vacuum states. Each of these vacua is like a separate valley in a cosmic mountain range, each with its own unique terrain defined by different physical constants. In one valley, the strength of gravity might be 1,000 times stronger. In another, electrons could be heavier than protons, preventing atoms from ever forming. Our universe, with its perfectly tuned constants that allow for stars and life, is just one single valley in this incomprehensibly vast cosmic range. So how did we end up here? The answer brings us back to the quantum fluctuations we have followed throughout this journey. During the inflationary period of the early universe, these random tremors in the quantum fields could have kicked our local patch of spacetime into one specific valley in the landscape, locking in the particular set of physical laws we observe today. Our reality is not a predestined masterpiece, but one possible outcome selected by quantum chance from an almost infinite array of silent, lifeless alternatives. This grand vision, however, stands on a foundation that remains frustratingly beyond our current reach to verify. The most significant criticism of string theory is its lack of testable predictions in our low-energy world. The strings themselves are thought to be so small that probing them directly would require energies a quadrillion times greater than what our most powerful particle colliders can produce. We are like sailors adrift on a calm ocean, trying to deduce the existence of individual water molecules by studying the large-scale properties of waves. We see the compelling mathematical beauty of the theory, the way it seamlessly weaves gravity into the quantum tapestry, but we cannot yet design an experiment to confirm that the fundamental notes of reality are indeed played on vibrating strings. Despite this, string theory endures as the most comprehensive framework we have for a theory of everything. It represents humanity's boldest attempt to read the universe's source code, to understand how every quantum fluctuation, every particle, and every force emerges from the harmonious vibrations of a fundamental string. It is a symphony waiting to be heard, its melody hidden just beneath the silence of the vacuum. From the foundational hum of the zero-point energy field to the speculative, vibrating strings of a theory of everything, we have journeyed across 30 breathtaking visions of reality. Each theory, from the cosmic hologram to the branching multiverse, presents a different facet of the same profound mystery, all unified by a single, restless engine, the quantum fluctuation. These are not mere mathematical quirks or ghostly abstractions, they are the active architects of our cosmos, the seeds from which galaxies sprouted, the potential source of our own consciousness, and the silent countdown on a vacuum that may one day rewrite its own laws. The grand tapestry of existence, from the vastest cosmic web to the flow of time itself, appears to be woven from these infinitesimal tremors. The universe's greatest secrets are not written in the light of distant stars, but hidden in the seething, probabilistic foam of the quantum vacuum, a foundational layer of reality where probability reigns and something emerges from nothing. So tell us which of these theories resonates most deeply with you. Do you see our cosmos as a holographic projection, a single branch on an infinite tree, or a simulation running on a cosmic computer? Share your thoughts on the nature of reality in the comments below. The conversation about our universe's deepest layer is just beginning.